Jai Hind everyone. I am Dublish, faculty of Akgec Engineering College in MC department. Today I am going to deliver a lecture of Introduction to IoT. The subject code of this Introduction to IoT is in MC department for KCA 043, and this lecture is valuable for all the BTech CSIT student and MCA students. So let's start. So what is IoT and what is the vision of IoT? The vision of IoT can be seen from two perspectives, internet-centric and thing-centric. So the internet-centric architecture will involve internet services being the main focus, while data is contributed by the objects. In the object-centric architecture, the smart objects take the center stage. And a conceptual framework integrating the ubiquitous sensing devices and application is shown as in figure 1. So, in order to realize the full potential of cloud computing as well as sensing, a combined framework with the cloud at the center seems to be most viable. This not only gives the flexibility of dividing the associate cost in the most logical manner, but it is also highly scalable. Basically, sensing services providers can join the network and offer their data using a storage cloud. And analytical tool developers can provide their software tools, artificial intelligence expert can provide their data mining and machine learning tools useful in converting information to knowledge, and finally, computer graphics designer can offer a variety of visualization tools. So, this is the conceptual IoT framework with cloud computing at the center. So, firstly, in cloud, we have three technologies, SAS, PaaS and IaaS. Through this, we can visualize computation and analytics stories. And in application of IoT is surveillance in critical infrastructure monitoring, in environment monitoring, health monitoring, and smart transportation. So, the wireless sensor network of things provide the security, quality of service, communication protocols, location awareness, and comprehensive sensing, etc. So, this is the IoT systematic showing end user and application areas based on the data. So, as we know, through IoT, we can sensing, analytics, and visualization tools anytime, anything, and anywhere in doctor term, in home personal user, in policymakers, and in industries. In home, we can say as per for the health, entertainment, security, utility, and appliances. And for transport, we can use IoT in logistic, traffic, parking, emergency service, highways. For community purpose, we can use IoT in factories, smart metering, business intelligence, retail, surveillance in environment. And for national purpose, we can use in defense, remote monitoring, utilities, infrastructure, and for smart grid, etc. Now, the question arises, what is IoT? So, basically, internet technology connecting devices, machines, and tools to the internet by means of wireless technologies. Over 9 billion things connected to the internet as we know. Things connected to the internet are projected to cross 20 billions in the near future. So, unification of technology such as low power embedded system, cloud computing, big data, machine learning, and networking. So, now the question is, how is this IoT technology come in the come in the market? So, in 2000, we are heading into the new era of ubiquity where the users of the internet will be counted in billions and where humans may become the minority as generators and receivers of traffic. Instead, most of the traffic will flow between devices and all kinds of things, thereby creating a much wider and more complex Internet of Things. So, this is the origin of IoT. So, the title of report was Internet of Things, discuss the possibility of Internet connected M2M connectivity network extended to the common household devices. So, some areas which we can identify as IoT neighbors are RFID, nanotechnology, sensors, and smart network. Next definition, we can say in general term, the IoT is a network of physical objects that contain embedded technology to communicate and sense or interact with their internal states or the external environment. So, moving on, the basic characteristic of IoT, it is efficient, scalable, and associated architecture. It is unambiguous naming and addressing, abundance of sleeping nodes, mobile and non-IP devices, and intermediate connectivity. This is the market share of IoT. In manufacturing, we can see it is 40.2%. In healthcare, we can see IoT using 30.3%. In retail sector, IoT is using 8.3%, and in security sector, IoT is currently using 7.7%. So, the application of IoT is which we generally use in business manufacturing field, in healthcare field, in retail field, or in security field. So, what is the meaning? How can we use IoT in manufacturing field? See, real-time analytics of supply chain and equipment, robotic machinery, and in healthcare, portable health monitoring, electronic record keeping, pharmaceutical safeguards, and in retail, inventory tracking, smartphone purchasing, anonymous analytics of consumer choices, and in security, biometric and facial recognition lock, remote sensor. So, evolution of connected devices. ATMs, VAPs, smart meters, digital locks, smart dust, smart cities, smart vehicle, smart healthcare. These all are the IoT based applications which we use today in our daily purpose. So, in ATMs, we can say these ubiquitous money dispensers went online for the first time way back in 1974. And in VAP, World Wide Web made its debut in 1991 to revolutionize computing and communications. And a smart meter, the first power meter to communicate remotely with the grid, were installed in early 2000. And digital locks, smartphone can be used to lock and unlock doors remotely. And business owners can change key code rapidly to grant or restrict access to employees and guests. Smart healthcare device connected to hospital, doctors and relatives to alert them of medical emergency and take preventive measure. And smart vehicles self-diagnose themselves and alert owners about system failure. It's smart city, city-wide infrastructure communicating among guests themselves for unified and synchronized operation and information dissemination. And smart dust, computers smaller than grain of sand can be sprayed or injected almost anywhere to measure chemicals in the soil or to diagnose problem in the human body. So, these are the modern IoT application like smart parking, structure health, noise or urban maps, smartphone detection, traffic congestion, smart lighting, waste management, smart road, river flood, smart grid, tank level, photovoltaic installation, water flow, silos stock calculation, parameter, access control and liquid presence. Forest fire detection, air pollution, snow level monitoring, landslide and avalanche prevention, earthquake early detection, water leakage, radiation level, explosive and hazardous gases, supply chain control, NFC payment, intelligent shopping application, smart product management. So, this is the expectation of IoT is application in millions, smart system in billions and sensor in trillions in next 20 years. So, this is the IoT enablers which we used in general purpose. Now, what is, next question arises, what is baseline technologies which we generally used in IoT? Baseline technology means a number of technology that are very closely related to IoT include machine-to-machine communication and web of things. So, now question is, what is machine-to-machine, M2M? So, basically M2M refers to communication and interaction between machine and devices. Such interaction can occur via a cloud computing infrastructure, example device exchanging information through a cloud infrastructure. M2M offers the means for managing devices and device interaction while also collecting machine and or sensor data. M2M is a term introduced by the telecommunication services providers and pays emphasis on machine interaction via one or more telecom communication network, example like 3G, 4G, 5G satellite public network. M2M basically is a part of IoT, while M2M standards have a prominent place in the IoT standard landscape. However, IoT has a broader scope than M2M since it comprises a broader range of interaction, including interaction between devices, things and people, things with application and people with application. It also enables the composition of workflow comprising all of the above interaction. So, IoT includes the notion of internet connectivity, which is provided in most of the network outlined above, but it is not necessarily focused on the use of telecom network. What is OT means word of things. From a developer perspective, the WOT enables access and control over IoT resources and application using mainstream web technologies such as HTML 5.0, JavaScript, Ajax, PHP, Ruby and Rails, etc. The approach to building WOT is therefore based on RESTful app principles and REST APIs, which enables both developers and deployers to benefit from the popularity and maturity of web technologies. Still, building the WOT has various scalability, security, etc. challenges, especially as part of the roadmap towards a global WOT. Basically, while IoT is about creating a network of objects, things, people, system and application, WOT tries to integrate them to the web. And technically speaking, WOT can be thought as a flavor option of an application layer added over the IoT network layer. However, the scope of IoT application is broader and includes system data not accessible through the web, example conventional WSN and RFID system. So, these are the terminological interdependence. IoT is divided in scale, people, autonomy, environment and synthesizes. So, when we talk IoT scaling, we use M2M. When we talk IoT in the terms of autonomy, we use CPS. When we talk IoT in terms of environment, we use IoE. And when we talk IoT in terms of people, we use IoP. When we talk IoT in terms of synthesis, we use Industry 4.0. Like in the market, robotics, virtual reality, workflow, scalability, these things used in Industry 4.0. So, moving on, IoT resulting in address crunch. So, it's estimated 50 billion devices by 2018. Reason is the integration of existing devices, smart devices as well as constrained nodes in a singular framework. So, integration of various connectivity features such as cellular, Wi-Fi, Ethernet with upcoming ones such as Bluetooth Low Energy, -7, Instron, IEEE 802.15.4 etc. So, the ITU vision is approaching reality as the present day network device have outnumbered human on earth. So, connectivity terminologies are basically IoT LAN, IoT WAN, IoT node, IoT gateway and IoT proxy. So, IoT LAN, it is a local short range communication, may or may not connect to internet, building or organization wide. IoT WAN is connection of various network segments organizedly and geographically wide connects to the internet. IoT node basically connect to other node inside the LAN via the IoT LAN, maybe sometime connected to the internet through a WAN directly. IoT gateway, a router connecting the IoT LAN to a WAN to the internet, can implement several LAN and WAN forwards packets between LAN and WAN on the IP layer. And IoT proxy perform active application layer functions between IoT nodes and other entities. So, this is the pictorial representation of IoT configuration of technologies IoT LAN, IoT WAN and IoT proxy via gateway and node. So, some of the IoT network configuration restricted to local areas analogous to normal LANs, WANs and proxy are shown in the previous figure. As we know, the node represented by green circle, here we can say node represented by the green circle have L means local link addresses of or LU local link address which are unique locally, and node within a gateway jurisdiction have address that are valid within the gateway domain only. The same address may be repeated in the domain of another gateway. Basically the gateway has a unique network prefix which can be used to identify them globally, and this strategy saves a lot of unnecessary address wastage, although the node have to communicate to the internet via the gateway. So, this is the gateway prefix allotment. One of the strategies of address conversation in IoT is use local address which exists uniquely within the domain of the gateway. So, these are represented by the circle in this slide. So, the network connected to the internet has routers with their set of addresses and ranges. So, these routers have multiple gateways connected to them which can forward packets from the node to the internet only via these routers. So, these routers assign prefix to gateway under them so that the gateways can be identified with them. Impact of mobility on addressings. The network prefix changes from 1 to 2 due to movement, making the IoT LAN safe from changes due to movements. And IoT gateway WAN addresses changes without changes in LAN address. This is achieved using ULA. So the gateway assigned with prefix which are attached to a remote anchor point by using various protocols such as mobile IPv6 and are immune to changes of network prefix. So this is achieved using LU. The address of the node within the gateway remain unchanged as the gateway provide them with a locally unique address, and the change in gateway network prefix does not affect them. Sometimes there is a need for the nodes to communicate directly to the internet. This is achieved by the tunneling, where the nodes communicate to a remote anchor point instead of channeling their packets through the router, which is achieved by using tunneling protocols such as IKEv2 Internet Key Exchange version 2. Now, what is gateway? So, IoT gateway with or without proxy responsible mainly for internet connectivity and for IoT LAN intra-connectivity. So, the upstream address prefix are obtained using mechanism like DHCP-v6 and delegated to the nodes using SLAC stateless addressing. So, LU addresses are maintained independently or of globally routable address in cases where internal address stability is of prime concern. Despite providing address stability, LU cannot communicate directly with the internet or the upper layer, which is solved by implementing an application layer proxy, and application layer proxies may be additionally configured to process data rather than just passing it. In nodes with no support for computationally intensive tasks, IoT proxy gathers data sent to the link local multicast address and routes them globally. Presently, the internet is mainly IPv4 based with little or no IPv6 uplink facilities or support. Due to the lack of universal transition solution to IPv6, lots of an unoptimized solution are being used for IoT deployment. These makeshift solution mainly addresses IPv6 to IPv4 translation, IPv6 tunneling over IPv4 or application layer proxies like data relaying. Now, what is multi-homing? A node network connected to multiple networks to improve reliability. In case of small IoT lanes, where allotment of addresses prefix is not feasible and possible, a proxy-based approach is used to manage multiple IP address and map them to link local address. In another, gateway-based approach is used for assigning link local addresses to the nodes under it. Providing source addresses, destination addresses and routing information to the multi-home nodes is the real challenge in the multi-homing network. In case the destination and source addresses originate from the same prefix, routing between gateway can be employed for the IoT gateway selection. Presently, IEFT is still trying to standardize this issue. So, this is the difference between IPv4 and IPv6. IPv4 developed in IETF 1974, whereas IPv6 developed in IEF 1998. The length of the IPv4 is 32 bits, whereas the length of the IPv6 is 128 bits. Number of addresses in IPv4 is 2 raised 32, whereas number of addresses in IPv6 2 raised 128. Notation of IPv4 is jotted decimal, whereas notation of IPv6 hexadecimal. Dynamic allocation of addresses in IPv4 is DSCP, and dynamic allocation of addresses slash DSCP-v6. IPv4 in IP second is optional, but in IPv6 original IP second is compulsory. The header size of IPv4 is invariable, but in IPv6 header size is fixed. Header checksum is header option based broadcast address. It is compulsory in IPv4, but it is not required in IPv6. Multicast addressing IPv4 does not provide, but multicast address IPv6 is provide. So, this is the pictorial representation of IPv4 header format. This is the destination address, source address, time to leave, TTL, protocol, header checksum, identification, flag, fragment offset, total length, types of service, IHL or variable. So, IPv4 emphasis more on reliable transmission as is evident by fields such as type of service, total length, ID, offset, TTL and checksum field. And this is the pictorial diagram of IPv6 header format. So the IPv6 header structure is more simpler as it mainly focuses on the addressing part of the source and the destination. It is concerned more with addressing than with the reliability of data delivery. So what is now most important question is what is sensor? So a sensor detects sensing changes in the ambient condition or in the state of another device or a system and forward or process this information in a certain manner. Or we can say a device which detects or measures a physical property and record, indicate or otherwise respond to it. This is the sensor basically performs some input functions by sensing or feeling the physical changes and characteristic of a system in response to a simulation. For example, heat is converted to an electrical signal in a temperature sensor, or atmospheric pressure is converted to electrical signal in a barometer. So this is all about today's lecture. In next lecture, we will study in detail what is sensor. Jai Hind, thanks.